What's up, class? This is our next online lecture series. This marks the introduction to Unit 2, Polynomials. So if you have any questions, feel free to reach out. This will be a multi-part lecture series delving into how polynomials affect real-world mathematical behaviors in the context of area and volume and economics. So if you have any questions, don't hesitate. And yeah, let's go ahead and get started. So to begin, let's answer the question of what is a polynomial. A polynomial is an expression that utilizes variables, exponents, and constants to define mathematical behavior. There are three conditions that must be met in order for a given term to be classified as a polynomial. First and foremost, all exponents must be positive and whole numbers. So if I take a look at this, for example, x cubed, that is permissible. That has an exponent that is positive and it is a whole number. However, if I had this, for example, these two terms are not polynomial terms because 1/2 is not a whole number and -4 is not positive. Let's take a look at the second condition. All variables must never be in the denominator. So if I had this, for example, this is permissible, right? Notice that my variable is in the numerator, so that is acceptable. However, if I had 1 over x cubed or 3 over x to the power 4, these two examples are impermissible. Notice that my variables are in the denominator. The final condition that must be met pertains to operations, and the only permissible operations are addition, subtraction, and multiplication. So, for example, if I had 3x squared, or if I had x plus 7, these two are polynomial terms. Notice that to connect my constants to my variable, they are connected via addition or multiplication. Impermissible operations include division, right? So if I had, let's say, 1 plus x over x to the power of 3, right? That's impermissible. Or if I had perhaps x squared divided by 7 squared plus x, that is also impermissible, right? Notice that these two terms are connected via division, right? That is not one of the permissible operations. If you have any questions regarding any of these conditions, please feel free to reach out. I will answer them as soon as possible. In your prerequisite course, you guys went over extensively linear equations, but if you need any additional help with linear equations, please refer to my prior online lecture videos regarding solving linear systems of equations and my first linear equation video. So we're going to begin our series pertaining to quadratics. Quadratics are functions with the highest degree polynomial of 2. So what do I mean by highest degree? What I mean is, if you take a look at any given polynomial function, there are perhaps multiple variables being considered. If the highest degree is to the power of 2, which is your exponent, then that constitutes a quadratic function. Quadratic functions define area. Your exponent, in the context of some sense of geometry, is defining how many dimensions you are existing within, right, on your plane. In that case, if it's to the power of 2, I'm only in the context of 2 dimensions, which in this case is a length and a width. And then the area, right, of any given sort of geometry problem will always be in the context of length and width. And in that case, it will be x squared, right? And then if we kind of take a look at what quadratic functions mean, is that if I'm scaling that area, whether I'm increasing or decreasing that area, that is what quadratic functions do in performance. They are defining the behavior of the given area that I have in my scenario. So the sort of the baseline structural quadratic function will look as such. It will look like ax squared plus bx plus c. Right? We can define what these constants mean. The a value is our scale, which we know to be the leading coefficient. We'll define what scale means in just a second, what it does. B is your linear coefficient or your slope. And then your C value is your y-intercept, so wherever you cross the y-axis. Before we begin looking at quadratic functions graphically, let's take a moment to define what the shape is. So formally, the shape is known as a parabola. All right, that is what a quadratic function looks like graphically. We call that shape a parabola. So let's take a look at a few parabola examples below. So if we take a look at our parabola function to the left, right, notice that our end behavior, which you guys took a look at last year, your end behavior is the furthest extent that your graph goes to in the y or x direction, right? So it's either your domain or range. And then notice that it's progressively increasing, right? And then take a look at the one to the right. Its end behavior, right, is progressively decreasing over time, right? The way we determine whether or not a given quadratic function will have a positive end behavior or a negative end behavior is based off of the a value. So recall that the a value was the value that was connected to the highest degree, right? Your scale or your leading coefficient. That leading coefficient directly impacts whether or not your graph will have a positive end behavior or negative end behavior. So if your a value is greater than 0, then your function will have a positive end behavior. So basically, if your a value is positive, and then if your a value is negative, less than 0, then you will have a negative end behavior. So those two aspects directly have a direct relationship. So let's move on to some other characteristics of quadratics. So notice that the parabola on the left, notice how it's more narrow than the one on the right. That is primarily due to the a value as well. So how the a value affects this depends on how large or how small that a value is. So positive or negative depends on whether or not it has positive or negative end behavior. However, if it's a larger positive value or a smaller positive value or a larger negative value or a smaller negative value will directly impact how wide or how narrow it is. So let's take a look at maybe a few points. Let's take a look at one on each of these axes. So at the value point of 1 on this parabola to the left, the corresponding y value is somewhere up here at 10. And then here on the right, it's somewhere maybe at like 0.01 maybe. It's hard to even decipher from this point of view, but it's definitely smaller than 10, right? And so if we take a look at this contextually at face value, we can determine that the parabola to the left is increasing at a quicker rate than the one to the right. And if that's the case, this a value is large, right? Which corresponds to a narrow looking graph. And in this case, our a value is small, which corresponds to a wider looking graph, right? So the next thing that we will kind of take a look at is whether or not our graph will shift to the left or right. this is a part of a parabola function that corresponds to our 0 points as well. So we'll kind of see these kind of play hand in hand with each other. If you have any questions about how to find your 0 points, which happens via the process of converting from standard form to factored form, please refer to my online lecture regarding factoring that was in your prerequisite series. So please refer to that lecture if you have any questions about how to factor. But let's take a look here at the function, the parabola to the left. It seems to be the case that we are crossing the x-axis at -4 and at 0, right? So our 0 points in this case are -4 and 0, right? And these correspond to a function that will look something like this. And I know that to be the case because if I set each of my terms equal to 0, x equal to 0, or x plus 4 equal to 0, that's already solved for me. But if I solve this one, x plus 4 equal to 0, I should get a value of x equals -4, right? Which is the case when I cross my x-axis. And then, of course, if I convert that to standard form, right, or if I distribute that x back into that x plus 4, I should get something that looks like this, x squared plus 4x. Notice that my point where I cross the y-axis is at 0. So this is like x plus 0. But we don't have to write that 0, so we just leave it like this. And then for this function to the right, this parabola is crossing the x-axis at 0 and at 4, right? And so my 0 values would be 0 and 4, which would correspond to x times x minus 4, right? Which is the case because if I solve each of these terms, if we prove this, that is solved, and then this would correspond to an x value of 4 that would solve that system, right? And so notice that inside the parentheses, if I'm adding 4 to the x, then that shifts the function to the left, and then when I'm subtracting in the parentheses, it shifts the function to the right. I know that's sort of counterintuitive, but if you solve for those terms within the parentheses, it will kind of make sense contextually of what's happening. So yeah, let's go ahead and move on here. So this final parabola shape, I'm just showing you where we're crossing the y-axis. So notice that it's crossing at 8. So that is my c value. If you have any questions about how c values work, you can always reach out to me via email, but that will always refer to your y-intercept when it comes to quadratic equations. We'll take a look at what happens when we have cubic equations now. So cubic equations, right, are a type of polynomial that defines volume. So that's to the highest degree of 3. And recall that for volume, I am not only dealing with a length and a width, but I'm also dealing with a height now. And so now that I'm dealing with the height, I'm no longer dealing with something in 2 dimensions. I'm now dealing with 3 different dimensions. So that's really important contextually. And cubic functions sort of have the same functional purpose, right? They are defining how my volume function is changing, right? How it's increasing and decreasing, the most possible volume I could have, the least possible volume I could have, right? Whenever my length or width or height are so disproportionate or completely disproportionate to each other where I can no longer hold volume, right? It's defining all of those points. And so let's take a look at what this means, right? So again, this is my baseline structure for a volume function. And my a value does not change definition. That is still the scale or your leading coefficient, whichever one you want to call it. And then the value of d now is my y-intercept, right? Your y-intercept is the value that does not have a variable attached to it, okay? Cool, now let's take a look at what happens, right, when I take a look at a few cubic functions, right? When I take a look at a few of these cubic functions, right, you can notice that for my end behavior ends in the positive direction. Right? If I read this left to right, I am slowly increasing over time, right? And then if I take a look at the cubic function to the right, I'm slowly decreasing over time. So this corresponds to your A value for cubics. So when your A value is greater than 0, when it's positive, you will have positive end behavior. Then your A value is less than 0 or negative, you will have negative end behavior, right? Those two have a direct relationship. Again, same sort of idea when you think about how narrow or how wide your cubic function looks, right? The more narrow it is, that means your A value is large. And then when it's wider, that means your A value is small. Right? And then in this case, right, I'm crossing the y or the x-axis at one point, and that's at -1. My y-intercept is at 1. Right? This function, right, recall that when I move to the left direction, inside my parentheses, I am adding, right? Because if I were to solve that, then my x value would be -1. And then because this is a cubic function, that highest degree is 3. I will teach you guys in later lectures. Actually, I'm releasing one called Advanced Factoring in the future, where I will teach you guys how to convert from factored form for cubics to standard form. There's a certain formula that we follow. So if you guys have any questions on these definitions for quadratic and cubics, please feel free to reach out. I'll answer those. Now let's take a look at how you would graph these. So for quadratic functions, there's a few rules that you must follow. For quadratic functions, you must know your y-intercept before you graph. You must know your 0 points. And you must know your extrema. Okay? Your extrema value is where you have a min or a max. So if we take a look back, let's take a look at this one right here. Notice that for my parabola to the left, I have a point in the graph, which is the lowest possible point I can go, right, before the direction changes. If it's the lowest possible point I can go, we call that a minimum. And if we take a look here, when we have negative end behavior, I have the highest point I can possibly go. We call that a maximum. Right? And these correspond to your A value. So if your A value is greater than 0, you'll have a minimum. If it's less than 0, you'll have a maximum. So if you need all three of those details before you graph a quadratic function. So let's check these off the list slowly but surely. I have my y-intercept, which is always my c value. So that checks off, it's at 64. Right? To find your 0 point, you need to convert from standard form to factored form. There are many different ways we can do that. We can find two values that multiply to c and add to b. We can use the quadratic formula. And then again in our advanced factoring lecture, I'm going to teach you guys how to factor when your a value is not 1. Right? So it could either be greater than 1 or less than 1, not including 0. I will teach you guys how to do that in later lectures. But for the sake of this lecture, I'm just simply going to use two different kind of ideas, and we can choose between one or the other. So in this case, we don't have to use quadratic formula. We can actually figure out two different values that multiply to c and add to b. These two values include 8, right? X plus 8 and x plus 8, right? 8 times 8 is 64, 8 plus 8 is 16. If we were to solve this, set the term equal to 0. We only need to set one of them equal to 0 because if we did the other one, we get the exact same thing. So the number that completes that term is -8. So now we have our 0 point. We can take it off. Last but not least, we need to find the extrema value. We can find the extrema value by a formula called vertex formula. Okay, your vertex formula tells you where that min or max is located for a quadratic function. So that is equal to negative b over 2a. You guys kind of saw this in your previous course as well, but that's what that formula is. So if I take a look here, I can plug in my b value, right? My b value in this case is 16, so negative 16 over 2 times 1, which comes out to negative 8, right? And then if you want to define your corresponding y value for that, you would just plug in negative 8 back into your function to give you y. So in that case, I'd have negative 8 squared plus 16 times negative 8 plus 64, right? That's 64 plus 16 times negative 8 is negative 128, and then plus 64. All right, so that comes out to, we combine 64 and 64, that's 128 minus 128. The corresponding y value is at 0. All right, so that is where our extrema value is. It's at the point negative 8, 0. And then if we take a look at our a value for this, if there is no a value that we can see, we assume it to be 1. 1 is greater than 0, so this function does have a minimum. So if we take all of our data, right, and utilize it to help us graph this equation, we should receive something that looks like this. Right, on the y-axis, we're crossing at 64. On the x-axis, our 0 point is at negative 8, which also happens to be our minimum. So our final graph looks something like this, right? Somewhere where I'm in fact crossing the x-axis at negative 8, and I am crossing the y-axis at 64. So if you had any questions on graphing quadratics, please feel free to reach out. But yeah, let's take a look at our final graphing example for cubics. So for cubics, things get a little interesting. There are a few details that I have to I have to keep obviated from this course, because you will learn those in later lectures and in your calculus courses. But for the sake of this course, it will be sufficient enough to just tell me where you cross on the x-axis and where your y-intercept is, and then tell me what your end behavior is. Those details will be sufficient. So we take a look here, right? I've already factored out an x, but your standard equation for this looks something like this. Notice that my highest degree is 3, right? And for this case, because I've already factored out an x, if I take a look at that quadratic term in my parentheses, that looks a little bit more manageable, right? I know two numbers that multiply to 15 that add to 8, right? So this comes out to x times x plus 3 and x plus 5, right? 3 plus 5 is 8, 3 times 5 is 15. So in this case, my y-intercept is 0, right? So that checks off. And then my 0 points, right, are, let's say we set x equal to 0, x plus 3 equal to 0, and x plus 5 equal to 0, each of our terms. Already solved for the solution. This is x equal to negative 3, and this is x equals negative 5. Right, so now I have my 0 points. And then last but not least, I need to figure out my extrema. The rule for cubic functions is that you will have at least one extrema, but at most you'll have two extrema, right? So at most you could have a min and a max, but in some cases you may just have a min or a max. It's okay, right? So let's take a look at what this will look like graphically. Notice that my a value is greater than 0, so my positive end behavior should be what I notice in the graph. And if we take a look at what this looks like graphically, if I draw my x and y axis, right, notice that I have 0 points at 0, at -3, and at -5. Right, my end behavior has to be positive, right? And so this should look something like this, right? Again, it may or may not have two extrema values, but on the safe side, we'll just plot out two extrema values until we can confirm whether or not it has two. Again, you will learn all of that in calculus. So let's take a look at some word problems to get some idea of how to solve these contextually. All right, so here's a practical example of quadratic. So let's take a look at this example together. A farmer has 80 meters of fencing to enclose a rectangular pen along a river. The riverside needs no fence. Let the width be x. Write an equation for the area in terms of x, and then find the value of x that gives the maximum area. So it already gave us a hint about what our a value is going to look like. Our a value is going to be negative because we're dealing with maximum behavior. And then I kind of drew it down here. Not too bad of a drawing if I say so myself. But down here I have a river, right, where I have a fence, which is defined by the 3 black lines, that is enclosing this river, right? And the perimeter of all of my fence is 80 meters total. All right, so just keep that in mind, right? That's all I have to play with here. And it said let the width side be defined as x, right? And for my length sides, we can think about this. My length is going to be pretty interesting here, right? My length in this case, we can think about it. I only have 80 meters to play with, and I have 2 length sides. I only have 1 width side, but I have 2 length sides. And so we can think about this as 2 length sides, right, that only have 80 meters to play with. So it's 80, right? Taking away 80 and disseminating that between 2 length sides, right? And because all of my sides are using this 80 meters, then I can share the value between these two as just x, right? That'll be permissible too. So if that's the case, to find the area of this rectangular or partly rectangular fencing situation, then I can just multiply x to 80 minus 2x, right? And then in standard form, this should look something like (80x minus 2x squared). And so now that I have an equation in terms of x, now I can find the maximum area. Recall that for maximum area, maximum is an extrema value. Right, and to find extrema value, I use the function negative b divided into 2a. And my b value in this case is 80, right? And then my a value in this case is -2, right? And because my a value is negative, right, then I know that I do have a maximum. So this comes out to -80 all over 2 times negative 2, which comes out to negative 80 over negative 4, which comes out to 20. So when I deal with 20, right, in this case, then I know I have the max possible area for this fencing. So let's figure out what that corresponding value would be. So if I take my 20, that's equal to x, and let's say I plug that back into my other term to figure out what that would be. In that case, I'm dealing with 20, which would go in for my x value, and then my 80 minus 2x, which is defining my side lengths, that should compute to 40. So I'm dealing with a 20 by 40 fencing situation, right? And that would provide me, if I plug in 20 back into my full function, I should get the maximum area possible. So if I have x, 80 minus 2x, plug in 20 back in for x, this would give me 80 minus 40, which would give me 20 times 40, which should give me 800. So 800 meters squared is the maximum area I could possibly have when I utilize a 20 by 40 fencing situation. All right. Let's take a look at a problem in the context of volume. So a manufacturer is designing an open-top box using a rectangular sheet of cardboard that measures 20 by 30 centimeters. Squares of each side X are cut from each corner, and the sides are folded up to form the box. Write the volume function, define relevant domain, y-intercept, min or max, and then interpret your result. So cool. If I have my cardboard sheet, it's telling me that I have a 30 by 20 situation going on, right? And I need to fold this sheet up, cardboard sheet, and then make a nice little square box out of it. So write my volume function. In this case, right, I'm dealing with some piece of cardboard, right, that needs to be folded up into a box. And then when I fold it up into a box, instead of just having one width side or one length side here, I will now have two of each. Right, really important detail to note, right? I'll now have two of each, which makes this a little bit more interesting when I try to define my volume function. So instead now of having just 30, now I have to take 30, right, and disseminate that evenly between two sides, right? So two sides that are proportional to each other. And then I have 20 that I also have to disseminate between two proportional sides. And then I have a height value, which we don't know, right? And so that height value that we don't know, I can just define as x. So 30, right, by 20, and then my height. Recall that for volume of a cube, it is equal to length times width times height. And so to find my volume function, I'm going to take x, multiply that by 30 minus 2x times 20 minus 2x. And in this case, I'm going to distribute out my values. This will come out to 600 minus 60x minus 40x plus 4x squared, all multiplied by x. And so that would be 600x minus 100x squared plus 4x cubed. Right? I just combined my like terms inside this parentheses and did that process a little more efficiently. So now this is my volume function. Notice that my highest degree polynomial in this case is 3, which is correct because that corresponds to a volume function, right? That is 3-dimensional. And so from here, determine the relevant domain. This is an interesting question, right? Domain is the all possible input values I can have. So it's asking me to figure out what are all the possible input values that I can have to ensure that I can create a box out of my 30 by 20 cardboard sheet, right? Let's think about this contextually. If I want to find relevant domain, all my possible input values. If I have my X and Y plane here, right, all possible input values would mean that my volume, right, could not be negative, right, because that's not possible. I only care about what's possible, all my possible input values, right, that are relevant to this function. For any given cubic function, it's, the all possible values or whatever I can input for the given function. But because this is talking about volume, then I only care about what's relevant, right? I only care about what's relevant. And so in this case, what's relevant is all values that exist in quadrant 1, because all values that exist in quadrant 1 are positive for both my input and output. So any values in quadrant 2, quadrant 3, or quadrant 4, we don't care about. Only quadrant 1. That is the only permissible quadrant we want. And so let's think about this. Domain is only asking for X values. So if domain is only asking for X values, at what point do I no longer have a positive X value? I no longer have positive X values in the quadrants 3 and 4. So I only care about when I have to cross the x-axis. Well, if I only care about when I have to cross the x-axis, well, that would just be my 0 points, right? So let's figure out where those 0 points are. And we can solve that by, of course, finding out our factored form and setting each of those terms equal to 0. So I had x times 30 minus 2x times 20 minus 2x. Set each of these equal to 0. Solve. This already has its 0. For this given equation, my x would actually equal to 15. This equation, my x would equal to 10. So now I have both of these zeros. Now in this case, where are all of my possible input values? Well, let's think about it. I need to make sure that I'm building a box where all my sides are proportional to each other, right? Within this given range, right, from 0 to 10, in this given range from 0 to 15, the values of 11 to 15 do not exist in this range. So if that's the case, 11 to 15 don't exist in that range, then I can't consider those either, even though they do exist in this one, because I'm making a box. And if I'm making a box, all my sides have to be in some degree proportional to each other. So my relevant domain in this case is from 0 to 10. Okay. So find the y-intercept and interpret its meaning. Well, if we take a look back here, notice that I did not have a d value, right? I had a c value, I had a b value, and I had an a value, right? But there, in fact, is no d value for this given equation. If there isn't a d value, then we assume it to be 0, right? And given the y-intercept is 0, that means, in this case, right, that I have no volume. Well, at the point where I have no volume is when I haven't folded the cardboard sheet yet, right? So that, in fact, would be the interpretation, right? My y-intercept is 0, and it's 0 because if I choose not to fold this cardboard sheet, then I'll have no volume. No volume corresponds to 0, right? And so determine whether the function has a min or max. Okay, so this is really important. We're thinking about this contextually. We had our function, we have our y-intercept, and we have our 0 points, right? And so if I were to graph this in some cases, right? And again, recall that cubic functions have at most 2 extrema values. I have a corresponding x point of 0, 0 point at 10, and at 15. My end behavior must be positive, right? Because my a value is in fact greater than 0. And so if that's the case, then my function more than likely looks like this, right? More than likely looks like that. So if this is the case, right, determine whether it has a min or a max. Or recall that my relevant domain was between 0 and 10, and between 0 and 10, I have a maximum value, right? And for this course, I will not have you guys search for those min and maxes because that will require a derivative, which you guys will learn in calculus. But if we take a look at where this value could possibly be, then we can figure out that in fact our maximum point is somewhere on our graph between 0 and 10, right? And in that case, our maximum value would be the most volume the box can hold, right? And I would recommend that you guys use your TI-84 calculators to figure out where that value is, right? You can figure out where that value is once you plug that in. And once you plug it in, you should come out to 3. It's 3 point something, and the corresponding volume is somewhere up here at the value of 1,000, maybe a little over 1,060 maybe, or maybe close to 1,055, I'm not sure, but it's somewhere between that. All right, and of course this is in centimeters cubed. So if you have any questions about how to solve these functions, please feel free to reach out to me. This is the first lecture in our online series regarding polynomials, so don't hesitate to reach out if you have any questions. I look forward to answering all of them, and have a great weekend.